All right, welcome everybody to Flat Earth Civil Discourse. This is episode 17 with my good friend Kyle Adams. Well, I say my good friend, I'm just kidding. We just met a few days ago. Kyle, can you please introduce yourself and then we'll get started.
Hi, I'm Flat Earth Kyle. So I don't know what else you want me to say.
Sorry, I had to cough. Well, you've got a YouTube channel. Like, how long have you had your YouTube channel? And I see you're gaining subscribers.
Yeah. I've trying to think about how long I've had it for. I'm not really sure. I've had it for a long time now, but it's been really gaining a lot of subscribers over the past year now.
Okay.
So, yeah.
And the thing is, one of the things I wanted to say to you about your videos is I really like your calm demeanor and then your very point by point presentation of, like, you know, here's the point I'm going to present, and then you kind of go through the evidence, and it's very nicely done.
Yeah, thank you.
Yeah. So I'd encourage anybody who wants to go to Kyle's channel. The link is in the description of this video. So let's talk about some of the like what brought you to Flat Earth. I always like to talk about people's origin stories.
Yeah.
You know, because I really want to see like you as a person, not as an adversary. So what brought you to Flat Earth?
I appreciate that. Yeah. Well, I really first heard about it at work and everything. Like, one of my coworkers and everything, an old Vietnam veteran and everything. He went and was telling me about, like, oh man, did you know there's actually like flat earthers out there? People who actually believe the earth is flat. And I first heard him and I thought that was absolutely crazy. And so I'm like, okay, I got to go see this for myself. You know, there's got to be a reason why they're believing this stuff. And so at first, you know, totally thought it was crazy. And then I started hearing a bunch of their claims. And it was like, wow, I never thought about that before. I never thought about that before either. There's actually some weight behind that. And so I started learning a lot more, you know, over time. And there's a lot of great videos out there that really just help me see things and everything. It was a lot easier for me after, like, my confidence in NASA was really shattered and everything. I really like the Potter's Clay, for example, and everything. It was one of my big inspirations there and everything. But a lot of my difficulties and everything with kind of learning it all about that stuff was everyone's video was like, you know, an hour long or something like that, except for like a few people and everything. But then they end up getting like really wordy and off on to other topics. And so I'm like, you know what? I really just want to create, you know, small points and everything that people can use in their different debates. And so, you know, if someone talks about this, okay, well, I've got a card I can play that I can share about that. And so that's kind of my whole idea there. And I like the whole building blocks. And so if I can keep it, you know, as building blocks that can be interconnected, that's kind of the goal. And so,
you know, I like how you have you know, it's sort of the structure of a university, and like, here's the curriculum, you know, and then you're just going step by step through the curriculum. So it makes it very digestible. You know, the videos are nice, short, and to the point. So I want to encourage you in your endeavor. Of course, I disagree with you, but
that's okay. That's okay.
Think, you know, like what you're doing and how you're doing, and I think that's admirable. And I appreciate that you're engaging with people who disagree with you in your comment section, and it's very respectful. And that really is, you know,
that's very difficult to find these days and everything, you know, on both sides and everything. People get very heated about it. And it's like, you know, there's too much rock throwing. And that was kind of one of the things that I really wanted to be different with, was I don't like all the rock throwing and everything. People are, you know, I don't need to snuff out your candle in order to say mine is the only true candle. No, that's not the way it works and everything. And so, you know, I try to just, you know, shine my own light and everything instead of trying to snuff everyone else's out. And so that's one of my major goals.
It's if we could, and you know, even by this conversation, if we can help inspire other folks, that you can actually have two people who disagree about the shape of the earth have a conversation and not tear each other apart. You know, like you seem like a reasonable person, and I try to be a reasonable person. So it's like, can't two reasonable people have a reasonable discussion about something that they disagree with? You know, So I think the answer is yes. So thank you for joining me here tonight.
Mm-hmm.
So do you want to start talking, like, this is not a debate. It was not designed to be a debate,
That's
but
fine.
you want to have like an informal conversation about some of the points that you raise in some of your videos, or
Well, ask away. Ask away. I am
okay.
totally open.
So one of the things that you've mentioned to me is that my videos on the flat Earth experiments, I call them flat Earth experiments. You say, well, they don't take refraction into account.
Yeah, that's a typical thing that I see a lot of, is people kind of forget to, they forget that we have an atmosphere that is all around us and everything, and that affects the light that passes through it. And so, that all needs to be factored into everything. You can't just pretend that the Earth doesn't have an atmosphere.
And that's a fair point. And I if you take a look at all the layers to the atmosphere, it starts to get ridiculous almost. It's like, how could we see through this with any bit of clarity? Because you got this layer and that layer, and each layer has different attributes, whether it's the moisture content, the temperature, the pressure, obviously, whether it is absorbing radiation or not. So you have all these layers, and so I totally get the point that you need to take into account these layers.
Yeah.
But I'm going to ask, what do we see? Like when we look at the night sky, say like the stars, do we see distortion? Like when this really at the stars?
That's why they twinkle, right?
Okay. So do we see big distortion? So and I think that was one of my comments to you about the twinkling. So if you were not an astronomer, like if you were just wanting to take a picture of the night sky, take a picture of the Big Dipper, you'd be able to take a picture of the Big Dipper just fine. No distortion. Now, does it matter? It doesn't matter where the Big Dipper is in the sky. Go ahead.
It depends on how you define distortion here and everything. The distortion can mean a lot of different things and everything. That's where I really like to open up the dictionary, and I love quoting the dictionary. People have make all sorts of claims and everything, and so I'm like, okay, well, let's just open the dictionary and just settle it that way and everything. It's easy to open it up and all done. People take science and there's no science there. I'm like, well, let's see what the dictionary says. You still there? I don't see you anymore.
Oh, I'm still here. I just changed the layout to you. Sorry.
Oh, you're fine and everything.
I'm focusing on you.
Okay, you're fine. So I was just saying, it's nice to open up the dictionary to settle things and make things straight. We speak the English language. That should be a basic thing.
So how much distortion are we talking about? Like, let's say the Big Dipper. I think it's like 15 degrees. Like if you take your fingers, like the what is that? I'm trying to do the surfing symbol. The 15 degrees. If you hold that up at arm's length, that's about the length of the Big Dipper. And so, how much distortion are we talking about when you say distortion?
Okay, so first of all, there's clarity kind of distortion, right? And so when we actually just look at the Big Dipper and everything, there's luminosity. Okay, and we discussed you discussed twinkling there, but there's also kind of where it's at. And so with the whole flat Earth model and everything, so much of it comes down to positioning and everything. The whole reason why the sun appears to set is the same reason why all the stars appear to set, and that's because of refraction. And so refraction itself can be a form of distortion. It's not, you're seeing something where it's not where it actually is, and so that can by definition be distorted. And so even though you can still see it, it's when it's not where it's supposed to be at, then that can be qualified as distortion.
Yeah, that's actually an important distinction. Is the measure of like how much distortion, or like how many degrees are we talking about? And obviously in the flat Earth community, their model of the flat Earth, the sun and the moon and the stars aren't where they appear to be. Because,
that's right.
And that was the whole thing with the Eratosthenes well. If you have three wells, then the lines don't triangulate on a single sun, right? They just simply any two lines will cross, but the three lines don't cross at one spot. And so I guess the flat Earth argument is that because of refraction, we are not seeing things where they actually are.
That's right.
Right.
That's right.
So have you thought about like how much of an error, like actual versus apparent, like how much of an error you're talking about with different observations?
Well, the hard thing about kind of knowing just how much of an error is you have to be able to know the exact place of where it actually is. And so unless you know where it actually is, you can't measure how wrong it is. Does that make sense?
Yeah, but you could spitball some ideas. Like one of the most common numbers is 3,000 miles for the altitude of the sun. Like if you look at all the flat Earth literature, if you look at all the books, that's the most common number for the altitude of the sun. And so
I've heard that one a lot too, and everything, but there's no way to verify it.
Sure, so. But like, let's just pick 3,000, and then you kind of run the angles. I mean, and you're welcome to pick another number, you know. But have you ever like tried to like run the numbers geometrically speaking? You know, if the sun were in fact this location, like what the error is, you know, from
well,
what
we can
see
speculate we can speculate all kinds of numbers. We can throw any kind of number we want in there and everything.
Sure.
And we can come up with something. But the question is the ability to verify that number. And so that's where the only way to verify that number, and I explain this in some of my videos there, is we have to be able to know all of the matter between us and the object that we're trying to measure the distance to. And so, we can't really go out and, measure all of the matter and everything, whether you live, whether it's a globe or whether it's flat Earth and everything. We just can't measure all of the matter between us and the sun. It's just not feasible. And so, I'm doing a video here this week actually about why the sun doesn't appear to shrink. And that'll be a really fun one and everything. And it kind of gets into a little bit of that.
Yeah, I'd be very interested to see that, because that's a big sticking point. Is flat earthers tend to talk about perspective, and one of the rock solid rules of perspective is if something gets twice as far away, it becomes twice as small. Yeah, and everything in between. And you could run the math, you could run the numbers. So
there's a few instances where people say, oh, well, we can see the sun shrinking here and everything. And, they've got like David Attenborough's shrinking sun and everything. But then they're like, oh, well, we got to see it through the filter and everything and on our camera. And so there's a lot of scrutiny about, some of these other observations out there. But I've got to say, that's kind of the exception, not the rule. We see it sometimes. We generally don't see that happen and everything. Normally we see like a full disc, going down below the horizon. So this week's video is going to be about, why that's our normal thing, that, why we see that usually. And so, it's a really good one. I really enjoy it and everything, but it kind of gets into this, what we're talking about here when it comes to, the things that we can measure and the things we can't measure. And that's where I try to be open about the different possibilities, but I'm not going to stick to something and everything unless I've got the way to verify it. Does that make sense?
Right. Yes. So let's, I know I'm going to push back on you a little bit, but I'm going to say one of the points about my Flat Earth Experiments videos is that I want people to say, I don't know what the shape of the Earth is. I'm going to make this very careful measurement, and then I'm going to compare the data that I get to the different models. The Flat Earth model and the Globe Earth model being the two most prominent models. I mean, there are other models out there, concave Earth and other things like that. And what I hope people to find is that their observation is less than half a degree error from what the Globe Earth would predict. Well, so do you have anything to say about that? Like, like no matter what you're measuring, it's less than half a degree error from what the Globe model would predict?
Oh, okay. The very careful thing here that you do is you got to really beware of the straw man arguments. The Flat Earth model should say this. According to the Flat Earth model, this is what it says. And I feel like you make too many of those kind of assumptions saying this is what the Flat Earth model says when what flat Earth model are you talking about? And so according to the flat Earth model, the sun should be shrinking. What flat Earth model says that? And so that's kind of that strawman thing. I don't think you're intentionally doing it. A lot of people just kind of do it on by mistake or something like that. But that's just something you got to watch out for. Oh, I can't hear you.
Sorry, my kid got tangled up in my headphone cord.
It happens. I understand.
So when we're saying the sun should shrink in the flat Earth model, what they're talking about is just the pure geometry of it.
I understand. Yeah.
So it's like take any model of the flat Earth, any map, any whatever, but have it be shaped more like a pizza than a ball, right? Mm-hmm. So if the Earth is shaped like a pizza, and then you place the sun anywhere above it, place the sun anywhere above it. Well, that sun has to get closer to some observers and further away from other observers. That's what people are saying about, it should get further, it should get smaller, it should get bigger.
It's making a lot of assumptions about the sun that we don't know. We don't know the size. We don't know how far it's moving. We know how far, it appears to move, but, how far it appears to move versus how far it is actually moving, they're two different things. And so,
yeah. So, and I don't know if you saw one of my last videos where one of the big arguments is like, we don't know exactly what the sun is. We don't know exactly, and that seems to be, it's kind of like an out, if we don't know exactly the diameter of the sun, therefore we can't say anything about the sun's size. Mm-hmm. And like, I think that's a little bit of a dodge because like, as long as the sun is not a hologram, as long as the sun is not a figment of your imagination.
Yeah.
So if the sun is a figment of my imagination, the sun's going to do whatever I imagine it to do. But if the sun is an actual thing, and even if it has an unknown diameter, like assuming that the sun is like a ball, it does look like a ball to, no matter how we look at it.
Yeah.
And maybe that's an assumption, but like, let's say the sun's a ball. Well, it would have a diameter, even if I don't know what that diameter is. So even if I don't know the diameter, you would think that if that ball got twice as far away from me, that it would get twice as small. Does that make sense?
I understand. It's kind of a big assumption and everything. You're assuming a certain size of the sun, and if that certain size is moving away and everything, then you're going to assume it's going to shrink and everything as perspective normally states and everything, right?
Yeah.
Yeah.
But I mean, it seems that it's not a prerequisite to know the diameter, the exact diameter. Does that make sense?
I understand what you're saying. Yeah.
Because like the point about my channel is that we can observe things. We can observe them carefully. You don't have to know the distance to the stars, but you can make careful observations of the stars, and then you can compare that to, and I'm not going to say like what the flat Earth model says, but just the pure geometry of it. The geometry of the flat Earth says that we've got the firmament and the stars are, like in the firmament or their lights in the firmament or whatever, but like
above it, below it, I'm not really sure,
but that's like a finite distance away versus the nearly infinite distance. It's not infinite, obviously, but like in the heliocentric model, the stars are an unfathomable distance away.
Yeah.
Like the stars aren't getting closer to an observer in Australia and getting further from an observer in say South America, like they would be if they were like part of the firmament structure. Does that make sense?
You're saying something about the stars being far away and sorry.
Well, like right, but I mean much further away than say the distance between the sun and the Earth.
Okay. That's kind of the thing about the stars here and everything, it can look really far away, but it can also just be really small and up close and everything. And so, there's a lot of different things that can kind of go into these things. And so, there's a lot of questions that I definitely have got. And I just, got to ask.
Yeah, no,
and trying to verify, that's the hardest part. But
the questions are good. And the thing is, like, if you have any questions that, like, off the top of your head, that even if you want to challenge me, the heliocentrist, like, we could talk about that, like some issues you have with heliocentrism. I'm happy to talk about that. I mean, I might not change your mind, but maybe I might bring some clarity to the debate or something. I don't want to, bludgeon you with, like, oh, this is the way it is, boom, 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 hitting you over the head. But
I understand.
But that's really why I present my flat Earth experiments, and then there's a bunch more, like on the solstice and on the equinox, etc. Lots of observations you can make, because I want people to compare what just the pure geometry of it, just the geometry of a flat Earth versus the geometry of the heliocentric model. And I would hope that you would think it would be a very big coincidence that every single observation is less than a half a degree error from just globe geometry. Does that, like, let's say the Earth were really flat. Well, how come the observation shows that it's, consistent with the globe?
Again, it's about kind of your model here and everything. What model are you comparing to? What's your flat? You keep talking about this flat Earth model, but you don't really describe. You've got this whole thing and everything. It doesn't seem like it's coming from a flat earther and everything, because where's your firmament? Where do you account for a firmament? That's totally off.
The firmament could be above the dome.
And how does that and how does the light get? How does that affect it and everything? Because we've got a lot of different flat Earth models out here and everything. There's the infinite plane and everything. Is yours an infinite plane and everything? Because I talk about that in one of my lessons here and everything. In lesson 7, I start off with the infinite plane. That many flat earthers out there believe in that and everything. But the vast majority of the flat earthers that I've ever talked to believe in a firmament that goes over our heads and everything. And that's going to affect the light that passes through it. And so, but I don't see any of your models there and everything that mentions anything about the firmament. Or how that light affects through it.
I'm pretty sure that at least in every flat Earth model that I've ever seen, and the thing is, and some people call me, grandpa, because I've been studying this for, I guess now over 12 years. I've been studying the flat Earth, the flat Earth model, the flat Earth debate. In every single model, the sun and the moon are below the firmament.
I've seen that.
Like if the firmament is a dome, say. And there's lots of conceptions about what the firmament is made of, whether there's water above it, all sorts of things. But in every single model I've seen, without exception, if it has a firmament, the sun and the moon are below the firmament. And so that's what I'm going with.
Okay, I've seen that. I've seen a lot of representations of what you're talking about. There's a lot of flat earthers out there, who believe that the sun is below the firmament instead of above it. And so, and a lot of my pictures and everything I try to include above it, because things make a lot more sense that way and everything for me, because that firmament, I can't really comprehend it as much. I'm not saying it's incomprehensible and everything, but under it, but I'm just saying that it makes a lot more sense that way, when it comes to the refraction wise and everything. When it comes to the sun setting and, the southern stars, I can't understand the southern stars unless the sun and the stars are above the firmament or in the
interesting.
firmament.
Yeah, because I did see your video where you talked about the Southern Cross.
Yeah.
I don't know if that may be a full video where it's just the Southern Cross, and how there was a presentation where somebody said, well, viewers looking south from Australia, South America, and Africa, or something like that, they're all seeing the Southern Cross. And then you're like, but wait a minute, somebody's in daylight, But I think one of the points that people were making in the comment section was that, but they're seeing it, and the Southern Cross isn't due south. The Southern Cross is not far from the Southern Celestial Pole. It's a pointer. The Southern Cross points to the Southern Celestial.
I understand.
Just like the Big Dipper, the end of the Big Dipper points to Polaris.
Yes, you're right.
But anyway, the point being that if you're looking north, like if I'm standing here, like I'm near Philadelphia, so if I'm looking north, it really doesn't matter the season of the year. If I could see stars, if I'm looking north, I will see the Big Dipper, not exactly due north, but it will be in my, not far from north.
Yeah.
And the point about the Southern Cross or even the southern celestial pole, which, there's no real star there, and there's no very visible star, is that you are looking due south from South America, due south from Africa, and due south from Australia. And at least two of those guys could be in night at the same time.
Yeah.
So they will simultaneously be looking in two dramatically different directions and seeing the same star, the same constellation.
And in my video, on the Southern Cross there and everything, I actually describe how refraction can do that and everything. It can make it so you can be looking in each of the different directions and all be seeing the same stars and everything. It's a pretty interesting observation there.
So would you say that refraction is not only changing the vertical position of things, like, for example, the sun appearing to set when it's actually not setting, so it's a vertical displacement because of refraction, but there's also a horizontal displacement?
There definitely is. Yeah.
Okay.
Refraction isn't just, a one-way thing and everything. Yeah.
So, because, with the heliocentric model, and you can actually measure this, people have with helium balloons, you can actually take pressure readings, air pressure readings, and air pressure is proportional to density. Maybe it's not exactly proportional, or at least inversely proportional to directly proportional to density. So it's like the denser the air, the higher the pressure. And so you can take these helium balloons and you can get them to be, like only like 2% of our atmosphere. So you have layers of atmosphere, with the most high pressure being what we breathe here at sea level. Yeah. And so the argument, or at least on the heliocentric side, is that if you have refraction, it's going to bend the light either down or it's going to bend the light up, depending on if you have like a desert condition where you have a temperature inversion. Yeah. But never that the light would get bent to the left or to the right.
Oh, it can definitely get bent to. Yeah, it goes. Yeah, it could be going in corkscrew and everything. It all depends on the environment that it's in. The light affecting it. But people are so used to just seeing it in just the two-dimensional view and everything, right? But it really depends on the environment. And when you're talking about here with the balloons and everything, it's unfortunate that whenever we take those temperature readings, they're all pinpoint temperature readings and everything, when we got to look at more of a 3D perspective here and everything and so I get into this conversation frequently about trying to measure the horizon. And okay, well, we got to go measure all of the refraction taking place on that horizon. We're like, okay. And so what are you going to do that? Are we going to just take one measurement and say, okay, well, this is what it is, and then just assume it is that way for all of from here to our horizon? No, the weather doesn't work that way. And so the only way to get an actual, reading is to take, every like square foot and everything measurement. And okay, well, this is the humidity, this is the temperature, and the pressure rate, and so you do that, and you can measure 1 foot here, 1 foot there, 1 foot there. But the problem is, the moment you do that and everything, all of a sudden, you look back and all of that stuff has changed already. The wind blows,
right?
And so you have to do it all simultaneously at the same time and everything, and not just at one point and everything, but at multiple points. And so you've got to get like this 3-dimensional fish net and everything going way out there, which ends up being really not feasible. And so it's very difficult to get accurate readings of all that.
I would argue impossible.
Yeah.
So like, you talk about the black swan. So you got this oil derrick that's 10 miles away. And I would say it is impossible to know the temperature, the pressure, the humidity, the particulate matter at every square foot or cubic foot of air between you and that platform. Like that's simply not knowable. I mean, even if you put temperature or sensors every mile for 10 miles, well, that's just 10 points. That's not an infinite number of points. So I get your point there. But something that I would like you to consider, at least in the heliocentric model, is that the atmosphere is remarkably transparent. And that's the thing I wanted to get back to with like the stars, is like when we see the Big Dipper does not change shape. Like no matter where the Big Dipper is in the sky, it could be close to the horizon, it could be high above our heads. The Big Dipper does not change shape. You can actually measure the
it just changes
angular
position
distance
and everything. Yeah.
Oh, it changes position, right? Its orientation, its location in the sky.
And so that's where I look at like the fixed thing, you know. And so the firmament is very fixed. We're not claiming the firmament is like moving all over the place. You know, it's not like, you know, being cloudy or anything like that. It's not getting fogged up. And so we should be able to see it clearly and everything. And the firmament is just only affecting the way it is, you know, its positioning in the sky. Does that make sense? And so,
yeah. Are you saying the stars are in the firmament or beyond the firmament or like?
Yeah, well, I think they're like in it or beyond it and everything.
Okay.
But there's a lot of things that get into that kind of realm and everything that I just don't understand and everything. And you know, I can't say that it's wrong because I don't understand it, because that's an incredulity argument there, a fallacy.
Right.
Yeah. Right. And so just because something's difficult to understand doesn't mean it's wrong. And so I've just got to, you know, there's a lot of things I've got to accept, and you know, with that. And so that was one thing I was going to include there in one of my videos here, is that, you know, while we may not know the answer to everything, just because we don't know something doesn't mean what we do know is wrong. You know, it doesn't invalidate what we do know.
Right. Can I put a comment up on the screen?
Go for it.
This is from SE. The fact that the Big Dipper doesn't change shape goes against your expanding universe model. So first off, it's not my expanding universe model, but what I would argue, SE, is that at human perspective, you know, where, you know, if you have to walk a mile, well, that's a long distance, but it's like at a global scale, you know, we talk in terms of millions of light years. And so when we're expanding, the question is expanding by how much? And is it at a human scale, it's like, oh, well, it's hundreds of light years per second or whatever. But in the actual distances between stars, on a, you know, human lifetime perspective, we don't really we wouldn't see that like constellations change in like a human lifetime. But yeah. So here's a question for you.
Yeah.
Are you familiar with the celestial sphere?
The celestial sphere.
Yeah.
Are you talking about like a map, a star map?
Yeah, a star map, but not just any old star map, a star map that can be painted on the inside of a virtual sphere. They actually have.
It's like a globe for stars.
It's like a globe for stars. I mean, they actually have them for sale. They're pretty expensive. I mean, it's hard to get one for less than $100. But basically,
Star Wars there and everything. You know, they're watching all the planets all around the room and everything.
Yes, like a holodeck. You can have like this like.
I don't know. I've seen those kind of things of the projectors that kids can get in their room as well, and everything that can show the stars all over the place. Right.
Like a planetarium will show like a hemisphere of stars, and I would say you stepping outside if it's a clear night, just stepping outside at night, you see a hemisphere of stars. Okay. Yeah. So the idea behind the celestial sphere is that if you have stars that are, let's say, practically an infinite, or not practically, virtually an infinite distance away, so far away that they may as well be all the same distance away. I mean, they're not. We don't argue that they are. Mm-hmm. But then they would comprise the inside of a celestial sphere, where the Earth is inside of this, or any observer is inside of this. And so the point that I'm trying to make about the celestial sphere is that every constellation has another constellation to its left, to its right, and above it and below it.
Yeah.
Including the Southern Cross, including, the Big Dipper and Orion.
That's how we're able to navigate and everything. You know, we kind of recognize this cluster of stars is over here and that one's over there. And so it's all fits together like a big puzzle.
Right. But it not only does it fit together like a big puzzle, it fits together like a big spherical puzzle.
That's because of, I understand that. It's just like the sun going over the Earth and everything every day. You know, we see it rise and we see it set and everything. And so that looks like a sphere, right? And so,
I understand. Or at least a hemisphere.
Yeah.
Right. So the point that I'm trying to make is that if the stars were either in the firmament or beyond the firmament, that wouldn't be a sphere. There wouldn't be a sphere of stars. That would be either a hemisphere or a dome of stars. Yeah. Like, so the point I'm trying to make is,
I don't really know. I can't really say, because it could all just be a big flat, thing up there and everything. I don't know how it all works and everything, but exactly, is it all like in a big like rainbow shape or anything like that? I don't know. So
yeah, but just getting, you were saying the three-dimensional jigsaw puzzle, but like every constellation has one next to it.
Yeah.
And so that means that there's no edge. There can't be an edge to the constellations, because like if you keep going, eventually you're going to wrap around, just like if it were on the inside of a sphere. So that's just the only point I wanted to make, is that all the stars, they do comprise a celestial sphere, and we can only see half of it on a clear night. Or half of it at one moment on a clear night. If you have, like 10 hours of darkness, you actually see a significant portion of the sphere as it rotates above us.
Yeah.
But anyways,
I've seen several models and everything that go through and talk about that on the flat Earth and everything. And you can watch the way the sun stays up in the sky and everything, and all of the stars and everything kind of go around in this like a perspective sphere and everything. Yeah. And I've seen plenty of models that can to show you how it all works on the flat Earth and everything. I might have one in my course there and everything.
I'd be interested because that's one of the big differences between the flat Earth and the globe Earth, especially in terms of stars, is the star. Nobody on the flat Earth is saying that the stars are wrapping around the Earth. Like, at least I've never seen that model. The stars wrapping around the flat Earth.
The firmament is kind of wrapping around, above it and everything, but not really under it that we're aware of.
All right, so let's shift gears a little bit, Kyle. Do you have something that you think is devastating to, say, the globe model, or something that you think is like really, kind of puts you over the edge? Like, there's no way I could believe in the globe because XYZ or whatever. And like, just a point for discussion, conversation.
Is there anything that really states that, it's got to be a flat Earth because of this? Is that what you're kind of saying?
Or it can't be a globe because of that, Okay.
Yeah, well,
and it
that's
doesn't
kind of my philosophy here is I don't really like to throw rocks. I'm not trying to go snuff everyone else's candle out and everything.
No.
That's not really what I go
just
for.
Purely for a point of discussion. Just to further the conversation, or if you want to talk about anything else, I'm up for talking about anything. Like, if you want to pick one of your recent videos that you want to say, hey, Charles, what did you think about this video? And
well, you were saying something earlier there about distortion above your head and everything, and it totally reminded me of the Stargazer project, and I shared that on my recent one on Stars in Front of the Moon. That was a horrible cartoon. Yeah, I agree. It was it was so like shocking because it looks so fake, and so that was a really fun a really fun one for me to look at. I had a lot of questions about that. It's an open discussion, open investigation, and so there's a lot I don't understand about what's going on there, and so a lot of people just instantly say, oh, it's totally fake. I'm like, oh, I totally agree. That's I really lean on it being fake as well and everything. But there's repercussions that go on both sides and everything. There's going to be some consequences as to it being fake, and there's going to be some consequences to it being real. And so it's just kind of, that's kind of what I saw there. But I was going to say with the Stargazer, the Stargazer project, they apparently sent the people way up there in the gondola and everything, on the high altitude balloon. The purpose of it was to be able to see the stars without all of the distortion and everything.
Yes, without the twinkling distortion.
Yeah. Well, it seemed like it was more than just twinkling, but I don't know. So I just had distortion, and so I didn't say exactly what kind of distortion. And so there's a lot of wiggle room that what did they mean by that?
Right. There's an essay that I think everybody should read. You could Google. I'm just going to type this in the chat. Actually, I don't have to type it in the chat. I can actually put it right there on the screen. Banner. It's called "The Relativity of Wrong" by Isaac Asimov. The Relativity of Wrong by Isaac Asimov. And I'm going to say add that. There we go. So the Relativity of Wrong. It's an essay. I think you should be able to find it somewhere online. And what it's talking about is when we make measurements and we say, oh, this measurement isn't accurate. And the question is, well, does it completely throw the baby out with the bathwater when we discover that this one measurement is not accurate? And then what Isaac Asimov is talking about is, well, how inaccurate? And that's really exactly what you were talking about with the stargazer, is like to eliminate the distortion or to eliminate refraction. Well, to what degree is a great question. I mean, it's a great question. And that's why I always tell people, like when they're talking about the flat Earth versus the globe Earth, they're like, oh, well, the horizon, we see too far on this black swan image. And I say, well, what's the actual error? What is the actual error? And the actual error is less than half a degree. And so,
okay, you're saying we see less than half a degree farther than we should? Or I don't know what that means exactly, because I don't really measure distance by degrees here.
No, but I mean, so for example, if we see this far platform and it is in front of the horizon, it's clearly in front of the horizon in the black swan image, that platform is appearing less than half a degree deviated from where it actually is.
Yeah. And so I always tell people that I'm not Nathan Oakley here and everything. And so, there's a lot of people out there. I think Nathan Oakley, he doesn't, I don't know, I've heard him say a lot of things about the refraction and everything. He tries to downplay that much and everything. But my whole argument is, that's my thing, and everything is, my whole argument is dependent upon that refraction there and everything. I'm, fully aware of that refraction and, all supporting, that's how the sun sets and everything is because of the refraction. And so, all of my entire argument is founded upon the refraction that we see in that image. That's what causes, so many things to work on the flat Earth.
Right. And I agree with you, but then I would say is compare that to what the globe predicts. And like Nathan Oakley, I mean, he hammers on the horizon all the time because it's like, is it the actual geometric horizon, or is it the apparent horizon, or is there some third horizon? And so, I think it's sort of muddying the water, because the only thing heliocentrists are claiming is that under extreme conditions, like the black swan image, the horizon may appear to be up to half a degree away from where it actually is. Which is not a huge error if you've got air, light going through, like we said, all these cubic miles of humidity, temperature, pressure, particulates, whatever. To have light bend only a half a degree after going through 10 miles, or if you look at these long distance mountain sightings, 100 miles.
Yeah, there's a lot of different things out there and everything. And so, you're trying to compare models again here and everything, but you're not really saying, what flat Earth model you're talking about, you're comparing to, so you've got to have that accurate comparison.
But pick a flat Earth model. Then that's one of the things I say on my videos all the time. It's like, I'm going to use, say, the Gleason's map, and I'm going to use, say, 3,000 miles for the altitude of the sun. But I also say, pick your own height, pick your own map, pick your own model, and then just compare that against the heliocentric model. So you've got your observations, and this is really what I challenge people to do. Go outside. You say, I don't know what the shape of the Earth is. It looks kind of flat to me. It feels kind of stationary. But like, make these very careful observations and then compare them to just the geometry of flat, or the geometry of the globe. And I say, pick your map, pick your model. I say that in a bunch of my videos. Pick your map, pick your model. If you don't like 3,000 miles for the sun, pick another height for the sun. Pick a range of heights for the sun, and see if that observation makes sense. Does that make sense? So I don't want to try to straw man, like, oh, the flat Earth model says this. It's like, well, just pick a flat Earth map. Pick your model, play with the model.
And I always think about that size and everything. There's, the size and distance and everything. You can get the same thing. I was just talking with my wife about that earlier today and everything, about how, the sun could be the size of a pea and everything, and, just be super magnified and everything. And we just, there's all these different things that we just don't know. Yeah.
Okay. So is there another topic you want to talk about, or did you want me to talk more about the Stargazer? Because I did want to mention that little cartoon, because I did try to do a YouTube search.
I have a full list of the source videos and everything. I have a full list of credits.
Yeah.
In my description there for anyone to follow it. I found that one with the British Path.
Right. I don't know how to pronounce it.
Yeah,
Pathe or Pate or something.
Yeah,
but,
it's British and everything. They have funny ways of spelling things and everything. But similar to French.
And I think that may actually be a French or something, because P-A-T-H-E does not look like an English word.
Like Pathe or Pathy.
Anyway, so what I would say about that is, that in today's rocket launches, they always have CGI mixed in, like when they're like, here's the rocket, but like, okay, so we can't really see the rocket anymore because it's so far away from the cameras. Well, then they'll switch to a view that'll be like, oh, here's a camera and it's right next to the rocket. Oh, and we see the fairings come off, and it's like, I think everybody knows that there really isn't a camera that's flying in formation with this rocket. Like, I don't think anybody actually believes that there is a camera that is flying in formation and seeing what the rocket is doing. Like, I think everyone knows that's CGI. Everyone knows that.
I think you're giving too many people too much credit and everything. I think there's far too many people who think, oh, wow, this is exactly it. This is the real thing. There's quite a few people.
So my point there is that here we have a scientific, expedition sending a rocket out up into space, and then they intercut that with an animation of like, oh, here's what the fairings look like when they pop off, right? And so with that British Pate or whatever that was, they're like, here's the Stargazer project. They're going to go up and they're going to see the stars, and then they cut to this little cartoon where, I mean, I don't know, it looked obviously to me like a cartoon. It was a bed sheet with a bunch of holes.
Totally looked like a cartoon. Okay, so there's a bunch of questions I asked there with it being a cartoon. Sorry, I don't want to cut you off here. So go ahead.
Well, no. But what I was, the point I was trying to make was that I don't think they were presenting that as footage, and I don't think they were trying to fool anybody. But I see what you're getting at, because they did show that star.
Yeah, why did they show that
in the crescent moon? So that's, and it was totally interesting what you said about the Islamic crescent. There's lots of crescents with the star.
And we see it all over the place. And it's just like, why are we seeing it all over the place? And that was my big question. Was this like, a common observation? Why are they doing this?
Right.
It seems totally bizarre. And so,
yeah, that is an interesting thought. A lot of people don't really understand where the Nazi swastika comes from. I mean, you show somebody a swastika and they're like, oh my gosh, that's so evil. But cultures across the world, literally worldwide cultures, have that symbol somewhere in their history. And it's like, well, how come that one symbol comes up? Do you know where the swastika comes from?
Yeah, it's from the Dipper, right?
No, it's not from the Dipper.
It's not from the spinning Big Dipper?
Nope.
Oh, I guess I was wrong. So.
It's from basket weaving. If you weave a basket and you look in the very bottom of the basket, you're going to see that crisscross, because it's like, this is going over, this is going under, this is going over. So that's why it's a universal symbol, because if anybody does any weaving, you're going to see that imagery.
That's the first. I've got to say, that's the first time I've ever heard that one before. Everyone's told me that. Oh, that's the Big Dipper going around the North Star and everything.
Yeah, I did see the Flat Earth video that had that in it, but that was also, there was a whole lot of anti-Semitism in that video, or in that by that channel.
I haven't even seen it.
So,
I thought that was like, I don't know. I've heard that more, or I've heard that way back before I learned about the flat Earth and everything. I learned about the flat Earth about 4 years ago. It's about like 4 years ago or something like that. Yeah,
and there's a lot of interesting content out there. I mean, I'm sure you watched Flat Earth Clues by Mark Sargent. What is it? 13 episodes of that, and there's a lot of interesting content. But the thing that I try to focus on for everybody is just try to get outside. Get outside, make some measurements.
Yeah, I'm getting ready to do a video here later. It's on my production queue here and everything about show me the math and exactly. Because everyone always says that. Oh, show me the math, and so I'm doing my video here where I'm talking about how math is like portrait painting. And everything. Math is like portrait painting. It's got, you have to be able to check it. If you're painting a cartoon and everything, and you've got your model over there and everything, your person posing for you, and your math doesn't look anything like your person and everything. There's an issue there. And so way too often people use math as a smokescreen, saying, oh well, I've got this and it looks all fancy and complicated, so therefore it must be right and everything, and they hide behind it. And if you want to have good math, you need to be able to describe, this part right here matches that part over there. You've got to be able to go between your painting and be able to match it up with the picture that you're painting. Does that make sense?
Yeah, but to a degree. Well, first off, I want to push back at people who are hiding behind a smokescreen of math, because I would love to see an example of that, because I could definitely see if somebody doesn't understand what's being presented. And I'll be honest, I'm a high school math teacher. I did not go further than just calculus in college. And so I know there's a lot of people watching right now who could just run circles around me with mathematics, because like my mathematical knowledge is very limited. I never went further than calculus. So you could show me like Einstein's field equations, and it's just going to be like, what is this? What language is this in? Because like I can't even recognize the symbols.
That's where I really try to simplify things. If I can't describe something simply and everything, then no one can understand it, and so it's kind of meaningless at that point. And so, it's only going to be meaningful to someone else who can understand it. Why would I be speaking, Spanish to you and everything if I don't expect you to be able to speak Spanish? Right.
But you would speak Spanish to a Spanish-speaking audience, or you would feel comfortable making a Spanish-speaking YouTube video, knowing that some people don't speak Spanish, but some people do, and the people who do will be receptive to your message, right?
Yeah.
So all I would say is I would push back on the smoke screen, because I would just be interested to see an example of that.
Okay.
But one of the things that I like to do
the video when I do that.
I'm sorry, what'd you say?
I said I'll keep that in mind when I make my video. And
but
I'll try and think about a good example on a smoke screen. So.
But with regards to like the one-to-one relationship, like you've got a portrait painting and then you've got the actual, say, person. So imagine the kid has freckles, right? Now, do you take a photograph of the kid and you compare that to somebody's painting? And I would be willing to bet that the freckles are going to be in the wrong position in the painting, and that the painting will have freckles, just the generic term freckles, right? But they're not going to be mathematically precisely placed on the kid's face. Like, who does that? Any portrait artist would be like, Yeah,
there are some really amazing portrait artists out there and everything. And everything, and they get down into very precise things and everything. They grid it all out and everything.
Right.
There's some very photorealistic artists out there.
But I hope you get my point, though. I hope you get my point in that. Yes, you can have a portrait and you can have the actual thing, but it's not necessarily going to be 100% accurate to the 10th degree.
I agree.
You're going to have.
We get that in math. I understand that and everything, because there's no way we can predict everything and everything. There's a cloud that just came by that day. There's a lot of different things that I just think about. If I were to go from point A to point B and everything in a car going at 60 miles an hour and everything, I'm going to try and calculate, how long it's going to, how long it's going to take me to get there, with this many stop signs and everything else. Oh, wait a second. My math didn't take into account I'd get a flat tire that day. There's a lot of different things that happen that just can't be predicted. And so, I understand where we're coming in from about the inaccuracies, here and there and everything. There's going to be some small little things that, but it's about getting as close to as what we can. And so that's where I'm just saying is, good math should be, like a painting and everything, right? We should be, looking at something and making that observation and trying to write down what we see. And so I really try to do the same thing with the flat earth and everything. The flat earth and everything is looking at something and we are trying to observe it and write down what we see. And that's where, all of my lessons there and everything from the very beginning is, okay, well, let's take a look at this. And so it's a systematic series of observations, right? It's a series of systematic observations and experimentations. That's, by definition, science. And so if it's not the systematic observation and everything and experimentation, then it wouldn't be science.
Well, that's exactly what my whole channel is about, is not just casual observations. Like, you go to the beach, you look at the horizon looks flat. Yeah, that's good enough for me.
Glass,
glass,
and let's really scrutinize, what is it we're looking at? And so, it's kind of, I always like that and everything. It's kind of like poetry and everything. We talk, how, let's really dive into that and everything, all the different meanings in this, and, see it, all the different connections as to what that could mean, and how each thing fits together. And I really liked, one of my favorite videos here that I did was concerning, I caught a glimpse of the different array of colors in the sunset and everything, over Las Vegas. There was on my infrared video. I really like that one, my infrared video. And I looked at the red and the orange and the yellow, and I was like, okay, well, we've got our prism here and everything. And this right here, this observation is telling us about the refraction. And I compared that to a rainbow and everything, and light going through a prism, and we're getting kind of the series of colors. And I'm like, okay, well, we can see this in the prism, and we can see it right up there, and we can see how that light is affecting, or how that light is going through it. And so the people say, oh, it's Rayleigh scattering and everything, and that can kind of tell us a little bit about it and everything. And I'm still kind of thinking that's just another name for this refraction thing that we're talking about here and everything. And so, we could get in a whole conversation about that. But
so I'll be very interested to see your math video, because that's obviously my specialty. But one of the things that I like to do, at least with the globe model, is show people that the math can be very, very simple. Yeah. So for example, sorry, my kid's yelling at me. There's fireworks outside. Yes, baby. For example, on the equinox, you take your latitude. So for example, I'm at 40 degrees north latitude, and just subtract that from 90. Mm-hmm. And that will give you the height of the sun at solar noon. Uh-huh. And so it's and that works anywhere in the world. Uh-huh. You take 90, subtract your latitude, that gives you the angle of elevation to the sun on the equinox. That's
where I get back into portrait painting here and everything. Yeah, it's I look at the observation and everything, and I just write it down and everything. I that's what I'm trying to paint, is that's the observation, and so that's what we're painting. And so but what it ends up being is when I'm writing down the same observation that you're looking at and everything, my picture is turning out to be a flat Earth and everything, and your picture is turning out to be a globe.
Yeah, but the math is more complicated on the flat Earth side to equal what we have in reality. That's the point.
Now you're pointing at the flat Earth and everything, and the flat Earth should be this way, but I don't know.
All I'm trying to say is that the math on the globe Earth side is literally 90 minus your latitude. That gives you your angle of elevation. Or you could say not even angle of elevation. You could say angle of from the zenith.
And I can do the same thing for the flat Earth here and everything.
But you'd have to counter refraction. You have to put in refraction though. Uh-huh. So you could do that with flat Earth, but the angles are going to be different for everybody on the planet. Uh-huh. Right? It's going to, and you have to have some, and I don't know, I've never seen the formula, but
that's what happens is, and that's what I think is a really good testing ground right there. Because we both are looking at the same observation, but it's about the cause. What's causing this observation? And so I'm saying that we're seeing this observation, that we're both agree upon and everything. Okay. We're seeing this observation because of refraction. Okay. And you're saying we're seeing this observation
because the Earth's a globe.
because the Earth's a globe and everything. And so it's about kind of evaluating the cause. And so it seems like you're trying to say, and it's not because of refraction and everything.
Yeah.
That's not the cause in your case, but it is the cause in my case. Does that make sense?
Yeah.
And so it's kind of taking, and so that's the real grounds right there that need to be tested and everything.
Okay.
Because we're both looking at the same thing, but it's all about the cause. What's causing it?
So Kyle, I try to have these conversations stay to about an hour, and right now we're all exactly at the hour mark. I would really welcome another conversation with you. So I don't want this to be farewell permanently. I'd like to invite you back on. So do you have any final words before we end the broadcast? We'll give you the last word.
It's been a pleasure. I really appreciate you and this whole conversation here. It's been great and everything. And I think you've been very respectful, and I appreciate that. And so,
well, I appreciate you, Kyle. You've got a bunch of good ideas, and I like the way you express yourself, and I'm interested to see your content. So thank you for joining us here. And I'm going to say to the rest of the audience, if you know of any flat earther who would like to have a civil conversation, like I said, this was not a debate. We weren't trying to bludgeon each other. We were just trying to talk some stuff out. So they can shoot me an email at flatearthmath@gmail.com. And please visit Kyle Adams' channel. Just type in Kyle Adams into the YouTube search bar. Actually, the link is in the description. So for Charles, Flat Earth Math, and Kyle Adams, I wish everybody a good evening. Thank you.
Thank you.